Hello everyone. In today's lecture, we are going to discuss about R-2R ladder DAC. In the previous lecture, we have discussed about binary weighted resistor digital to analog converter. And let us have a quick recap on analog to digital converters. Why we need analog to digital converters? So all the natural signals which we need to process are analog in nature. Let it be biomedical signals or electrical signals or a seismic signal or any noise signals, communication signals. All these are analog in nature. But the systems nowadays has been improved to digital. Right now we use digital systems rather than analog systems because of its advantages. The digital systems cannot process analog signals, so it is required to convert the analog signal into digital signal, and then we have to give it to a digital logic system. Now the digital logic systems or the digital signal processors will convert the digital signal and then will give digital signal as output. But digital signals are cannot be read by us, and so it is required to convert the digital signals back to analog signals. So we need digital to analog converters and the receiving and the other end, and the transmitting end we will be using analog to digital converters, and then in the opposite side we'll be using digital to analog converters. So in digital to analog converters, there are different types of digital to analog converters, and we'll be discussing about two. Weighted resistor DAC has been discussed earlier, and in today's session we'll be discussing about R-2R ladder DAC. R-2R consists of a parallel and series resistors connected in cascade to form an operational amplifier. Inverting or non-inverting form can be used depending on the polarity of the output voltage that we want to get from. R-2R ladder resistors act as voltage dividers along with the entire network, with the output voltage dependent on the input voltages. And this is an example of R-2R ladder structure and R-2R ladder DAC. If you see here, see the inputs are being given to this inverting terminal, and here we have the feedback. Now we have to find the Thevenin's resistance value. So how will we calculate the Thevenin's resistance? So if it is 0, we'll be connecting this to the ground, and if it is 1, we'll be connecting to the supply. We'll be using Thevenin's theorem, through which we can obtain an equivalent circuit of the concerned resistance network. A Thevenin circuit consists of Thevenin resistance and a Thevenin voltage, which can be placed in circuit and still works the same as the original resistance network. The total output voltage of 3-bit R-2R ladder network can be calculated by considering only one high bit at a time and summing the individual voltages of each bit using superposition to obtain the transfer function of the DAC. And see, this is a simple 3-bit R-2R ladder structure. So first we need to find the output equation. For that, we have to view the circuit from, let me consider this part, and we have to view the circuit. In order to find the Thevenin's value, we have to view it from this side. Right? When you view from this side, will be to find the Thevenin's, we'll be connecting these two. And so we have given the V reference here, and R and 2R like this. Then if we see here R parallel to R, V Thevenin, the value V reference is given as V reference by 2, and the resistance we are 2R into 2R divided by 2R plus 2R, right, which gives R. So that 2R is been replaced. This 2R is being replaced with a R. With an RR. right? Here, so we have R. We have found that the Thevenin's voltage is V reference by 2. Now we have to draw the remaining circuit, these two resistors and these two 2R resistors, which we have drawn in this part. Now again we have to consider this circuit, and we have to look the circuit from this side in order to calculate the V Thevenin. So here it has been done, and if you see here, when you add these two are 2R, this is 2R, right? And here we have the V reference by 2. V reference by 2. So once again, when we simplify, we'll get these two R, instead we'll be getting a single R, and V reference was mentioned as V reference by 4. See, V reference by 4 was received. You have to see the bit locations when it is being received. And finally, all these two are in series. We have to calculate the equivalent resistance. V reference by R will be the Thevenin equivalent voltage. Now consider, after these circuits, after this is another example. After making connections, right? If you see here, when the LSB is 1, the reference voltage is V reference by 8. When the second bit is 1, it becomes V reference by 2. And the MSB, when it is made 1, it is written as V reference by 2. Now, when we calculate the voltage, then it is V reference into the whole sum of this, because this is purely a summation. It's been done here. So sum is being given to inverting amplifier, right? So here we have the output equation, and since it's been given to the inverting amplifier, we write minus RF by R into V reference into the whole values. Now this is for your assessment, and thank you.